Welcome to our session on feature scaling in data science. Today, we'll look at two of the most common scaling techniques: normalization and standardization. These are fundamental preprocessing steps that make a huge difference in how machine learning algorithms perform. Machine learning algorithms are highly sensitive to the scale of the data. If one feature has values in the hundreds, while another is in the thousands, the larger scaled feature tends to dominate the model. For example, if we compare age ranging from 0 to 100 against income ranging from 0 to 100,000, algorithms like k-nearest neighbors or clustering will give far more weight to income, just because the numbers are bigger. Similarly, gradient-based models like regression or neural networks converge more slowly when features are on very different scales. Feature scaling ensures that all features are treated fairly, improving both performance and interpretability. There are two main approaches to feature scaling: normalization and standardization. Normalization rescales data into a fixed range, usually between 0 and 1. Standardization, on the other hand, centers the data around the mean and adjusts it to have a standard deviation of 1. The choice depends on the type of algorithm and the distribution of your data. Let's look at each one in more detail. Normalization takes your data and compresses it into a fixed range, usually between 0 and 1. The formula subtracts the minimum value and divides by the range, so the smallest value becomes 0, and the largest becomes 1. For example, if our feature is age with values 20, 40, 60, 80, and 100, normalization transforms them into 0, 0.25, 0.5, 0.75, and 1. This technique is particularly important for distance-based models, like k-nearest neighbors, or for neural networks, where keeping input values in a bounded range improves training stability. Standardization works differently. Instead of compressing into a fixed range, it transforms the data so that the mean is 0 and the standard deviation is 1. The formula subtracts the mean from each value and divides by the standard deviation. For example, if we take incomes of 30,000 to 110,000, the standardized values become negative and positive numbers, centered around 0, such as -1.26, -0.63, 0, 0.63, and 1.26. Standardization is most useful in algorithms that assume a normal distribution of the data, like linear or logistic regression, principal component analysis, or support vector machines. Here's a side-by-side comparison. Normalization fixes values into a range, while standardization has no fixed range. Normalization depends on the minimum and maximum values in your dataset, while standardization depends on the mean and standard deviation. Normalization is generally better for distance-based algorithms, while standardization works better with Gaussian-based algorithms. One important caveat: normalization is highly sensitive to outliers, while standardization is less so, though still not completely immune. So when should you use each technique? Normalization is best when working with neural networks, deep learning, or distance-based methods, like k-nearest neighbors. Standardization is the better choice when your algorithm assumes a normal distribution, such as linear regression, logistic regression, PCA, or support vector machines. In practice, though, many data scientists try both approaches and compare results, since performance can vary depending on the dataset. To wrap up, feature scaling prevents one feature from dominating others, simply because of its scale. Normalization rescales values into a bounded range, usually 0 to 1. Standardization centers the data around 0, with unit variance. Both are essential preprocessing steps that ensure fair feature contribution and better model performance. Choosing the right method depends on your algorithm and the nature of your data. This concludes our module on feature scaling. We will soon see some examples of this in the labs.